FirstElement Fuel operates one of the most important hydrogen refueling networks in the United States. Through its True Zero brand, the company built and operated retail hydrogen stations across California intended to support fuel cell electric vehicles at scale. These were not experimental prototypes. They were certified, safety-approved, commercially funded stations built to serve real drivers under real operating conditions. And yet, despite this maturity, the network has struggled with reliability, uneven utilization, and long periods of reduced availability. The instinctive explanation often points to hydrogen technology itself. Electrolyzers, compressors, or storage systems become the convenient culprits. But when the system is examined honestly, electrolyzers are not where this story breaks. The failure occurs at the interfaces, where hydrogen infrastructure collides with supply chains, operations, and the electric grid. This matters because FirstElement did not fail quietly or marginally. Its challenges became visible to customers, regulators, and investors alike. Drivers experienced station outages. Public agencies convened workshops to address reliability. State evaluations documented downtime and supply disruptions. These outcomes were not caused by a single broken machine. They were the result of a system that required multiple independent infrastructures to work perfectly at the same time, and rarely did. At the heart of the misunderstanding is a persistent myth in clean energy development, that if each component works individually, the system will work collectively. Hydrogen refueling disproves this assumption. Hydrogen stations sit at the intersection of electricity, industrial gas supply, mechanical reliability, safety regulation, and transportation demand. Weakness in any one of these domains can halt the entire operation. FirstElement's experience shows what happens when these interfaces are not treated as first-order risks. Public reporting and state evaluations make one fact clear. The most immediate and documented causes of downtime in California's hydrogen refueling network have been hydrogen supply disruptions and station reliability challenges. When centralized hydrogen production or delivery systems experienced technical failures, multiple stations went offline simultaneously. Even stations with functioning dispensers and storage could not operate without fuel. This created cascading outages that had nothing to do with electrolyzer efficiency or dispenser design. Hydrogen simply did not arrive. Station equipment reliability further compounded the problem. Hydrogen refueling systems operate under extreme conditions: high pressure, frequent cycling, strict safety tolerances. Compressors, valves, chillers, and controls must perform flawlessly. Maintenance is specialized. Spare parts are not interchangeable with conventional fueling infrastructure. Early station generations struggled to achieve the uptime expected of retail fueling. Over time, reliability improved, but the damage to customer confidence was already done. Economics intensified these technical challenges. Delivered hydrogen in California has been expensive, volatile, and sensitive to upstream disruptions. When hydrogen prices rise, station margins compress. When margins compress, maintenance budgets tighten. When maintenance slips, reliability declines. This feedback loop is not a technology failure. It is an economic fragility built into the system design. So, where does the grid enter the picture? Not as the primary failure mode, but as a critical stress multiplier. Hydrogen stations are electricity-dependent systems. Even stations that receive delivered hydrogen rely on power for compression, cooling, control systems, and safety equipment. Electricity access is not optional, and in California, electricity access is not guaranteed. Grid interconnection for hydrogen stations is a non-trivial process. Developers must navigate utility studies, service upgrades, and approval timelines that can stretch for years. These challenges are well documented in state permitting guidance. Grid connection is often separate from local permitting and funding approval, meaning stations can be physically built but electrically constrained. This alone can delay commissioning and inflate costs. But the more subtle grid risk emerges during operations. California's grid is increasingly managed under scarcity conditions. Utilities and grid operators prioritize reliability above all else. Loads are categorized, curtailed, or restricted based on system conditions. Hydrogen refueling stations do not occupy a protected category. They are not hospitals. They are not emergency services. They are discretionary loads competing for capacity in a constrained system. This does not mean hydrogen stations are routinely shut off by grid operators. There is limited public evidence of systematic curtailment being the dominant cause of FirstElement's outages. But it does mean that hydrogen stations operate without firm guarantees on power availability during peak stress events. For a system that converts electricity into stored energy, this uncertainty matters. It introduces operational risk that is rarely modeled correctly. Grid access also affects economics indirectly. Service upgrades increase capital costs. Demand charges raise operating expenses. Limited flexibility constrains when compression can occur. These factors do not shut stations down overnight, but they erode margins and resilience over time. In a system already strained by supply and maintenance challenges, grid complexity becomes another fault line. This is why framing the FirstElement experience as an electrolyzer failure misses the point. Electrolyzers were never the bottleneck for retail hydrogen stations. Many stations did not even rely on on-site electrolysis. The bottleneck was coordination across infrastructures that were never designed to work together seamlessly. The hydrogen supply chain expected consistent production and delivery. The stations expected consistent fuel availability. The grid expected flexible, schedulable loads. Drivers expected gasoline-like reliability. Each expectation was rational in isolation. Collectively, they were incompatible. This incompatibility is what ultimately constrains utilization. Stations may be mechanically capable of high throughput, but throughput is meaningless without uptime. Uptime requires fuel, power, maintenance, and regulatory compliance simultaneously. Remove anyone and utilization collapses. This is why utilization metrics alone are misleading indicators of demand. Low utilization does not always signal lack of customers. It often signals lack of system availability. From a financing perspective, this is lethal. Investors underwrite based on projected throughput, uptime assumptions, and operating margins. When outages occur due to supply disruptions or reliability issues, revenue volatility increases. When electricity costs fluctuate or access is uncertain, cost volatility increases. These risks are difficult to hedge. As a result, expansion slows, not because hydrogen vehicles lack potential, but because infrastructure risk remains poorly contained. Regulatory structure exacerbates the problem. Responsibility for hydrogen infrastructure is fragmented across agencies. Transportation regulators focus on emissions reduction. Energy regulators focus on grid stability. Funding agencies focus on deployment metrics. No single authority owns the full system outcome. Hydrogen stations exist between jurisdictions, absorbing risk from all sides without receiving commensurate protection or coordination. This fragmentation explains why improvements in one area rarely solve the whole problem. Newer stations may be more reliable. Supply chains may diversify. Grid planning may improve incrementally, but unless these improvements are synchronized, the system remains brittle. The FirstElement case is therefore not a cautionary tale about hydrogen's technical viability. It is a warning about infrastructure integration. Hydrogen refueling is not just another load on the grid. It is not just another fueling station. It is an interdependent system that amplifies weaknesses across energy, transportation, and industrial supply chains. This distinction matters for the future of hydrogen. Many regions are planning hydrogen infrastructure under the assumption that lessons learned in California were purely technical. They were not. The lessons were structural. Building more stations without redesigning how supply, power, and operations interact will reproduce the same failure patterns. This is why so many hydrogen projects struggle to reach final investment decision. The barrier is not belief in hydrogen. It is uncertainty. Uncertainty about uptime. Uncertainty about supply continuity. Uncertainty about operating costs. Uncertainty about grid interaction. Investors do not reject hydrogen because it is unfamiliar. They reject it because system risk remains unresolved. At this point in the analysis, it becomes clear that better technology alone will not rescue hydrogen refueling. Higher efficiency electrolyzers will not fix supply fragility. Faster compressors will not overcome downtime. Smarter controls will not override grid constraints. The system must be redesigned around resilience, not just performance. This is where Renee Energy points developers, consultants, and investors toward H2 Hub by Renee Energy. Not as a sales destination, but as a structured environment for examining hydrogen projects through real system constraints: supply continuity, operational reliability, grid interaction, and financial exposure, before capital is committed. Hydrogen projects do not fail in isolation. They fail at interfaces. The FirstElement experience should not be read as a verdict on hydrogen's future. It should be read as a diagnostic. The technology worked. The demand existed. The failure occurred where systems collided without coordination. Until hydrogen infrastructure is designed with these collisions in mind, stations will continue to look built but behave fragile. And that is the real lesson from California's hydrogen refueling network. The electrolyzer was never the villain. The villain was assuming that complex infrastructures would align on their own. They never do.